Okay. So I'd like to welcome everyone to the monthly meeting of the Memphis Astronomical Society. We are a public service nonprofit promoting interest in education and astronomy related sciences. We have a number of ways that you can get in touch with us. We have a website, we have a Facebook group, we have a it's not called Twitter anymore, is it? It's called X um, uh, feed, and we have a YouTube channel, and we keep all of our meetings, and we take videos of all this stuff and present those on our YouTube channel, so you can catch a lot of past meetings there. I'd like to welcome you all. We have a great speaker lined up for tonight, and a subject that is of particular interest to me, and I know a couple others in our organization that are ham radio operators. We're going to talk about radio astronomy tonight. Just another segment of the electromagnetic spectrum to be analyzed. So let's see, what do we got next? So if you would like to join the Memphis Astronomical Society and doing so for the low price of $25 a year provides what funding we need to maintain things like our websites and our newsletter and then help support our public outreach programs where we try to go put on observing sessions and what have you. And although it doesn't really take money for that, it just helps us not have to worry about websites and stuff and insurance. And speaking of our outreach events, please don't think you need to be an expert astronomer to participate. We need everybody, people at all levels in our hobby, to help with our outreach events. So we provide outreach events to the general public, and there is a form on our website you can go to and fill out and request an event, and we will try to round up volunteers to help support that. Most of the time we can. There are occasions where we run out of volunteers. We get more requests than we have volunteers to support them. So let's see. Okay, it's more about the requests. This is all Jeremy's stuff. He normally goes through all this. This is some pictures from our last observing event at our dark sky observing spot, Burton's Sugar Farm. And I guess this is just some snapshots of some of the people that showed up. I was not able to make it, so I'm not sure what else to report about this. You can see our calendar of events and on our website. And for this month, let's see, we've got our meeting tonight. We've got observing session at Burton's tomorrow night, and odds are that's going to be that's going to be a go. That call is generally made Saturday morning sometime. Someone, our VP of observing, will check the weather, make sure the clouds aren't going to be rolling in, and make the final go, no go call for observing tomorrow night. But we'll have a session at Burton's if it's not going to be cloudy. Sunset's expected at 7:15, so you might want to get there before that so you can set up without being in the dark. Of course, even at sunset at 7:15, it's not dark really for quite a while. See, the following week, there's an Arkansas Dark Sky Festival, the 14th, 15th, and 16th. I think Jeremy's going to that. Some other MAS members, I think, are going to participate in that event. And we also have, oops, I didn't mean to do that. We also have another observing session at Burton's. Then toward the end of the month, we have our astrophotography group meeting at 7 o'clock on Wednesday night, the 20th. Our MAS board meeting on Friday night, the 22nd. And then Saturday night, we have a public observing session in Collierville. This is typically these are meant to be mentoring sessions. So if you've got a new telescope, you're not sure how to use it, you're not quite confident enough, you want to get out to our dark sky site, meet us at Hinton Park in Collierville before the sun goes down. We'll help you get everything set up and try to enjoy your telescope. Let's see, what else we got? This is, there you go. There's a whole slide dedicated to that. So Sunday, September 23rd at 7:30 p.m., Hinton Park. I got a slide about the Dark Sky Festival in Arkansas. There's a link to their page about it, and I can try to put that in the chat in a bit, maybe, if you're interested. Village Creek Star Party is coming up. That's we do that twice a year, once in the fall, once in the spring. Pretty big event over at Village Creek State Park in Arkansas. It's about 45 minutes to an hour west of Memphis, and pretty decent skies. So you might want to come over there and bring a telescope and help us show the campers and other people that'll be there, or just come and look through the telescopes yourself. All right. Scopes needed. Here's where it's at. This is Memphis. From Collierville, it's an hour and 13 minutes to get to the Delta Q restaurant. So if you are going with us, you can meet. Where's the guy's time on here? Send us an email, but typically a bunch of us get together at Delta Q, which is a barbecue shop in Forest City, Arkansas, have some dinner, and then drive on up to Village Creek, which is actually right here. This is the state park. Somebody didn't know what they were doing. All right. So we have some new members and got several slides. So I'd like to welcome Jim Dotson to the Memphis Astronomical Society. Is he on here tonight? There is a tradition of joining the MAS and then not showing up at the next meeting. It's just how it goes. Thomas Conley, welcome to the Memphis Astronomical Society. Glad to have you. Deshaun Harris, I apologize for mispronouncing names. William Frog, I guess. I hope that was right. Welcome to the MAS. Matthew Mulqueen, welcome to the Memphis Astronomical Society. Jonathan Saunders, welcome. Nayak Sneha, welcome to the Memphis Astronomical Society. All right, one of the benefits of being a member is you get our electronic monthly newsletter, which is quite honestly professionally published. We've got a guy that is absolutely wonderful at doing this and produces a wonderful newsletter. And wow, you didn't even know this. I didn't know they stuck that in here. So you have a little article here by me. So it's got to be good. Must be interesting. And then if you want some MAS swag, we have a I forget the name. Here, Cafe Press, and you can get lots of stuff with the MAS logo and on it. And we also have logos for our Memphis Astronomical Society astrophotography group. We have, in some sense of humor, called them masfits instead of misfits. So it's Memphis Astronomical Society, and then .fits is the image file format that we all use for processing astrophotography images. So there was a play on words there. The masfits are our astrophotography group. We've got lots of cool stuff. Check it out. I don't know. I think at some point they donate some money to us, but more than anything, that gives. If you want to show your pride in being a member of the Memphis Astronomical Society, there you go. Go have at it. All right. So we have fall elections coming up. Elections are December. I think that's right. And then we finish nominations at the November meeting, and then have a final election at the December meeting. So if you are interested in being a member of the board of directors or one of the officers, currently Jeremy Veldman is our president. Sarita Joshi is our secretary. Merrill Miller is our treasurer. VP of programs is Freddie Diaz, and VP of observing is Mark Matthews. And if you want to, I promise you, running against any of them would be, they'd probably be glad to see it coming. So feel free to try to get nominated to one of those positions or any one of the 5 other just board member positions. There are 5 board positions to go with this group, and I'm on the member of the board and not an officer anymore. And yet I still seem to have more to do than I got time for. But we need help, and we would love your input, especially young people. Let's see, what is this about? Okay, so this is about our astrophotography focus group. Get it? Astrophotography focus. We're nothing if not humorous. Our next meeting will be September the 20th. It's always a Zoom meeting, and it'll be at 7 p.m. Central. And you're welcome to attend these. There's always a link on our webpage to that meeting when it gets close. And if you have any interest in astrophotography, or even if you aren't sure whether you have any interest in astrophotography, certainly come along and attend this meeting. We have a wide range of skill sets and skill levels in here, everything from the absolute beginner to a couple of very well seasoned professionals who do some amazing work with some of the tools that are available to work with. So we really like to look at it as an opportunity to put teachers and learners together. So trust me, in this hobby, once you get to know some stuff, there's really nothing more fun than teaching it to somebody else or showing other people. So feel free to join us for Memphis Astrophotography Group. We have Memphis Astronomical Society solar glasses, and we will be giving these away in preparation for the upcoming solar eclipses, the annular eclipse in October and the total eclipse next April. We will have them at our next in-person meeting, which will be October 6th at Rhodes College. So show up and pick up some solar eclipse classes ready for the October eclipse. All right, well, that gets us down now to our tonight's program. And all right, so Miss Ellie White is our speaker tonight, and the program is about the Green Bank Observatory and how it's played a central role in the field of radio astronomy, astrophysics in general, over its long and productive lifespan. In this talk, we will go on a tour of the observatory, exploring modern and historical instruments. Oh, that'll be cool. On site in incredible ways that they have contributed to our current understanding of the universe, from discovering black hole at the center of the Milky Way to founding the search for extraterrestrial intelligence. We will also learn about the Green Bank Telescope, the largest fully steerable radio telescope in the world. It is carrying on the GBO's history of excellence in scientific discovery, technology, and education. And oh, by the way, don't walk in there with a cell phone or even a microwave oven. So I'm looking forward to hearing about it. I've studied a little bit about it myself over the years, just because of my ham radio hobby and astronomy hobbies kind of mixed together, and think, building something that'll pick up that was it the hydrogen shift of one electron in the hydrogen shell at a certain frequency. I forget what it was, but I thought about building a horn antenna and setting up and trying to do that at some point. So anyway, radio astronomy can be a lot of fun, and certainly is going to be a very interesting talk. Ellie, thank you, and welcome to the Memphis Astronomical Society. And I will stop sharing and turn it over to you.
All right. Well, thank you so much for the kind introduction, Rick, and thank you all very much for having me today. I'm really excited to talk about the Green Bank Observatory, and it sounds like I'm actually going to do a little bit of introduction about radio astronomy as well, but it sounds like probably several of you might know more about it than me. So if I'm going too slow, just tell me to speed it up, and I will happily do so. Yeah, so but first of all, I also want to say you guys are doing really cool stuff. It's given me all kinds of ideas to bring back to astronomy stuff here in West Virginia. So this is really glad I got to kind of hear what you guys are up to, because it's really neat. Yeah, so like Rick said, my name's Ellie White. I recently got my bachelor's in physics from Rush University, which is a small school here in West Virginia. Yeah, so I've been doing radio astronomy research since 2016, and mostly with the Green Bank Observatory, and also some other places like the Berkeley SETI Research Center, which is focused on kind of looking for aliens, which we'll talk more about here in a little bit. And also I've also done some work with the National Radio Astronomy Observatory's Central Development Lab, and some other places like that, and all really cool places to get to work. I'm super lucky for that. So yeah, so currently my position, I'm actually working for a nonprofit, a West Virginia Alliance for STEM and the Arts, because kind of education is also something I'm super passionate about. So I'm working on that and planning probably to continue my education here soon as well. So that's kind of just a little bit of background on where I'm coming from. So yeah, so I of course I'm going to talk about the Green Bank Observatory, which I've basically kind of somewhat grown up there, live only a couple of hours away. It's a great place to kind of have almost in your backyard. In West Virginia, 3-4 hours drive is nothing. So to get somewhere like that. So yeah, we're super lucky to have this resource in our state, and yeah, just in the region. So I'll go ahead and get started. And if you have any questions throughout the presentation, I can check the chat at the end, but if you want to like interrupt me and ask something like as we're going, feel free to unmute and ask whatever you want. All right. So I always start off this presentation by just kind of zooming out a little bit to talk about astronomy in general. Of course, you all are all here because you love astronomy and you know that it's important. And so some of the reasons that I just think that astronomy is so important, just for society and just for us individually, is for two main reasons, really. Of course, as part of doing astronomy, you get all kinds of like exciting, fascinating side benefits, like Wi-Fi was developed accidentally by a radio astronomer. So you get all these kind of great technologies that develop as you're doing pure research. But of course, doing research and kind of asking questions about our universe is just kind of super important on its own, even without these kind of like practical benefits, just for kind of the view it gives us on our universe and kind of where we came from, where we're going, and what we might find out there. So of course, I know I'm preaching to the choir on this one, but I always just like to take a step back and just look at why astronomy in general is so kind of exciting and inspiring. So we were talking about this a little bit before everybody signed on. Of course, astronomy across the spectrum is really important. So we call this multi-wavelength astronomy. So of course, just in case there's any folks in the room, they're kind of new to physics and astronomy kind of concepts. I just wanted to talk a little bit about the electromagnetic spectrum. So of course, when we talk about radio waves, we're not talking about sound. We're actually talking about a type of light that's much redder than red. So it has a much longer wavelength and a much lower frequency than optical light. But it is in fact a kind of light. Of course, as you go up the spectrum from from long wavelengths to short wavelength, you go from radio to infrared to optical, and then you get bluer than blue or more purple than purple as ultraviolet, of course. Then you have X-ray and gamma rays. And astronomers study objects in space using all of these different kind of wavelength regimes or parts of the spectrum. And so if you'll notice something about this graph, there's something really special about both radio and optical astronomy. So what this graph is showing here is you can see where these kind of like wavy lines kind of get cut off here at the bottom. Some of them go all the way to the ground. Some of them get cut off somewhere like in the atmosphere or like above it. So the great thing about radio astronomy and optical astronomy is that radio waves and optical light can actually get through our atmosphere, which is not the case for a good portion of the infrared spectrum and a good bit of ultraviolet, X-ray, and gamma rays. So if you want to study infrared, ultraviolet, X-rays, or gamma ray objects in space, emissions from those parts of the spectrum in space, then you have to send like your telescopes actually above a certain layer of the atmosphere in order to actually be able to do those observations. Of course, that's really expensive to do. So the great thing about radio and optical astronomy is that you can just stick a telescope on the ground, make it as big as you want, or as big as practicality will allow, and just do some great science. So that's kind of just a brief introduction to the electromagnetic spectrum. So you might be asking, why is it actually important that we study objects at all of these different wavelengths? Why is it not enough to just take a picture with an optical telescope and then call it good? Because you can get a ton of information from optical telescopes, like the kind that that you all use, like the Hubble Space Telescope, like all these really famous telescopes that we're familiar with. But as it turns out, different parts of the spectrum, like radio waves, infrared, etc., give us entirely new picture on objects in the universe that we couldn't learn about using just like just optical or just radio. You need kind of a collection. So I just thought this was a really cool kind of demonstration of that concept, because each of these images is of the same object, the Crab Nebula, which actually several societies on Earth, of course, recorded when it happened. So like the ancestral Puebloans that lived in Chaco Canyon are thought to have created a petroglyph that represents when the supernova went off. But anyway, I'm kind of going off on a tangent there. The important thing about this image is you can see when you look at this object in X-ray, you can actually see that there's a pulsar at the center of this nebula. You can't see that really in any of these other images. In the visible light, you can see all these kind of like interesting tendrils of gas, and radio, you can see kind of almost an interesting like shell structure. So there's all kinds of different information you can get from each of these images, each of the different parts of the spectrum. And that's why multi-wavelength astronomy is so important. So what's special about radio waves in particular that's different from some of these other types of emissions? So radio waves allow us to see through dust. So unlike optical light, which kind of gets stopped by dust in our galaxy, things like that, radio waves just pass right through it. So that lets us kind of have X-ray vision and see some objects that we couldn't using other parts of the spectrum. Radio waves also allow us to look at cold objects really well. They allow us to find atoms and molecules in space that are emitting at unique frequencies. They show us some really weird and exotic objects that we'll talk about here in a minute that we kind of first discovered using radio. They help us learn about explosions in space, like supernova explosions, things like that. And they also allow us to look for extraterrestrial life, extraterrestrial intelligence. And of course, some of these things you can do with other parts of the spectrum, but for one reason or another, radio waves are really especially helpful. So just to talk a little bit about just kind of a brief history of radio astronomy, I wanted to talk about some of my favorite people from the history of the field. So radio astronomy started out back in the 1930s. It was 1931 or 32. I always get it backwards. But Carl Jansky was kind of the first radio astronomer ever. So he wasn't an astronomer, actually. He was a radio engineer with a background in physics working for Bell Labs. And he was trying to solve the problem of why there was static in the phone lines. And so they kept noticing this pattern of static that was showing up like, on this really like this pattern every 24 hours. So Carl Jansky built this really cool antenna and took a lot of observations, and turns out that weird static was actually radio waves coming from the Milky Way. So he kind of made that discovery. And people kind of initially noticed it and thought, oh, that's cool, but then not much happened with it for several years until Kurt Reaper came along. And he was the first person to build what we think of as kind of a modern radio telescope that looks kind of like a parabolic dish, almost like a TV satellite dish. So he built this great big dish in his mom's backyard with some of his buddies. So I'll talk more about what he did here in just a minute. But Kurt Reaper was a really interesting character, and I could give a whole presentation on him just for all the interesting things that he did. But so Ruby Payne Scott is another early radio astronomer. She started her work during World War II. She was probably the first woman radio astronomer. She had a background in physical sciences, and she actually contributed a lot to the development of array technology, so the process of combining multiple radio telescopes stacked like one big radio telescope. So she did a lot to make that possible in its modern form. And she also discovered a type of solar radio bursts. That was kind of really her specialty, was solar radio emissions. So she did a lot of fascinating work there, and kind of laid a lot of the groundwork for a lot of the technology that we have today. And then Barbara Williams is another fascinating figure. There's actually not that much information like available about her, but I'd love to learn more, because she was one of the first, if not the first, African-American woman to get a PhD in astrophysics. And she was, and her area of research was actually neutral hydrogen in extragalactic sources, which Rick was actually just talking about, the neutral hydrogen line, which we'll talk more about here in a minute. So she did some really interesting work there. And I just wanted to kind of talk about all four of these folks. There's lots more people that we could talk about, but their contributions really were pretty significant. So more about Kurt Reaper now. So if you go to the Green Bank Observatory, one of the first telescopes you'll see is Kurt Reaper's radio telescopes. This is one of the historical instruments on site. It's not actually operational right now, but it's not a reproduction. It actually, they transported Reaper's telescope from its initial site in Wheaton, Illinois, which is right outside Chicago, to Green Bank and rebuilt it and then painted it red, white, and blue for the bicentennial. So of course he built this telescope in 37, and then he kind of went through a interesting experiment process of building several receivers. Receivers, of course, are basically radio cameras. So they're the things that you use to kind of detect the radio waves. And you usually mount those like up at the top here. So he built a receiver first at 3300 megahertz, and then one at 900 megahertz. Neither one, he didn't have very much luck with either one. But then finally he built a receiver centered on 160 megahertz. And he was able to finally pick up signals from the Milky Way, make a map, which is the first kind of detailed map that we have of the Milky Way in radio. And so, yeah, so that's so Bert Reber did some really interesting work there. He also kind of studied the sun. And so his work really kind of laid the groundwork for everything that came after. So yeah, so radio astronomy as kind of a field of research didn't really start to take off until World War II-ish. So several places kind of around the world, the UK, Australia, places like that started getting pretty advanced in their radio astronomy technology, and the United States decided, okay, we need to kind of get in on this. So the government decided in the 1950s that they were going to create a national radio astronomy observatory, and they decided to locate it in Green Bank for a couple different reasons. One, it's rural, it's remote. Very little people lived there then, as is true now. And so what that means is that there weren't very many, fewer people means fewer electronics. Electronics cause problems for radio telescopes, which I'll talk about here in the next slide. But the other reason is the mountains. So normally when you think about an observatory, you think, okay, well, you should put a telescope at the top of a mountain. That way you're looking through less atmosphere, and so on. And that's true, and that's helpful it is helpful for radio telescopes to be at higher elevation. But the reason that, but in Green Bank, the telescopes are actually located in the valley. So why is that? Well, it's actually because the mountains provide a shielding effect from electronics in the surrounding region, which is kind of like a built-in, shield, which is pretty cool. And it was also chosen because it's not too far from DC, and that's where kind of the NSF is, and so that's kind of, they wanted to be, close enough that it was only like a day trip or so. So that's kind of the rationale that went into choosing Green Bank. So one of the most famous things about the observatory, if you've ever read an article about it or just kind of are familiar with it in some way, the National Radio Quiet Zone is kind of a super famous thing. It covers a 13,000 square mile region. And within the National Radio Quiet Zone, this 13,000 square mile part of it, the restrictions are actually not that strict. Basically what it means is that if anybody wants to build a cell phone tower or any other kind of like big transmitter, they just have to go through an approval process to make sure that their design and their placement of their antenna is compatible with the restrictions based on the needs of Green Bank, as well as the Sugar Grove station, which is located nearby. But there are much more stringent requirements within a 10-mile radius of the Green Bank Observatory. So this is kind of like a radio astronomy instrument zone. And so within that region, you're not supposed to have like wireless electronics like microwave ovens, cell phones, Bluetooth, things like that. Of course, people still have them. There's really not much that people can do about it. You can't really cart people to jail for having cell phones. So they do the best they can in terms of like patrolling the area, trying to replace any kind of like faulty electronics that are creating like bad signals with better equipment. So like one example is that I think someone had a dog blanket and it was shorting out and causing like really bad interference that was messing up the telescope's data. They actually located the source of that interference and actually bought the people a new dog blanket that wouldn't short out and cause problems. So I always like that story. There's all kinds of stories like that. But within the site itself, so like actually when you get to the observatory, there's a gated region where all the telescopes are. It's kind of like a telescope zoo. Behind those gates, you're not allowed to have like everything has to be powered down. It's totally restricted. If you want to install any equipment out there, you have to actually go through a testing process in the anechoic chamber on site. So it's a whole big deal. And I actually lived, so I actually worked for the observatory for 8 months. I think I forgot to mention that. But I lived on this road here, and I had a phone that was wired to the wall. I didn't have a microwave oven. And my internet was also like, wired internet. So that was pretty interesting. But that's kind of how everyone there is, everyone that lives in the employee housing has to abide by those rules. So it's really kind of in some ways it's a perk. So it's really cool. But yeah, so that's kind of what the quiet zone is about. So yeah, so just kind of continuing our history of radio astronomy in Green Bank. The first telescope that was built on site was actually called the Tatel telescope, also called the 85-1, because it is 85 feet in diameter. And when we talk about the size of a radio telescope, when we say so many feet or so many meters, we're talking about the diameter of the dish. So a lot like, if we talk about a 12-inch Dobsonian, it's the same deal. So yes, this telescope was 85 feet in diameter. It was built from a kit, and it was completed in 1959, 2 years after the observatory was dedicated. And it later served as an element in the Green Bank Interferometer, which is a collection of telescopes on site that work together, like we were talking about a little bit ago, that Ruby Payne Scott kind of worked on that technology. But I'll discuss that more when we talk about the GBI. So the 85-1, or the Tatel telescope, is one of my favorite telescopes at Green Bank because of the really cool history that it has. So I mentioned kind of earlier in the presentation, and Rick mentioned when he was kind of reading the introduction, that the search for extraterrestrial intelligence was actually born in Green Bank. So before 1960, lots of people had thought about the idea of whether we might find life beyond Earth, and some people had even come up with like ideas for experiments, but no one had ever really systematically searched for signs of intelligent life beyond Earth in a really systematic and scientific way. Of course, you could talk about Percival Lowell and his kind of Martian canal studies, but that was of course ended up not being all that scientific. So as interesting as a story as that was. So really Frank Drake's project in 1960 was kind of the birth of SETI. So Frank Drake, of course, was actually one of the first astronomers at Green Bank. So he kind of became famous as the founder of SETI. His first project was called Project Ozma. And that consisted of pointing the 85-foot telescope, Tatel telescope, at two different stars, so Epsilon Eridani and or Eridani, whichever you prefer, and Tau Ceti. And so he spent several months just monitoring those two stars, looking for signs of any kind of like what we now call technosignatures, which are signs of an advanced civilization in the form of like a clearly artificial radio signal. So the only signs of life that he found were signs of life on Earth. So he detected lots of radio frequency interference, which is radio signals generated by us, but he did not find aliens that time, unfortunately. But that didn't stop him, thankfully. So the next year, 1961, he organized the first ever SETI conference in Green Bank, and invited supposedly everyone in the world that was interested in scientifically searching for life beyond Earth. Ended up being 11 people. And yeah, but it was a really interesting group. It included Carl Sagan when he was really young, and Melvin Calvin, who ended up winning the Nobel Prize in Chemistry, and learned that he won the Nobel Prize while he was in Green Bank for that conference, which I think is just the coolest thing ever. But yeah, so while Drake was kind of preparing for this workshop, he was like going through all the different factors that are involved in thinking about life beyond Earth, and he ended up writing the Drake equation, which is this thing. And what the Drake equation basically allows us to do is estimate how many detectable civilizations might exist in the Milky Way. And so the factors range from, the rate of star formation in the galaxy, what fraction of stars have planets, what's the number of planets in a solar system that could support life, what could be potentially habitable. One definition of that might be they're in the Goldilocks zone, which of course is the region where a planet might be able to have liquid water based on its temperature. And it kind of goes on from there, talking about factors ranging from what fraction of planets develop life, fraction of planets where the life becomes intelligent, what fraction of the life becomes detectable, which means that of course we think about life on Earth. Dolphins are intelligent, like the great apes are intelligent, like orangutans, gorillas, etc. But we couldn't detect any of those species from outer space because they're not like emitting radio signals. So when we're talking about looking for intelligent life in space, we're actually talking about looking for life that has that emits electromagnetic radiation in some way. So it's not just, we can't necessarily just detect them if they're not like kind of announcing their presence in some way. So the last term of the equation is really interesting. It's L. So that's actually the expected lifetime of a civilization, or the period over which it's communicating. So for Earth, we've only been detectable to other civilizations if they're out there for about 100, 150 years, because that's how long we've been transmitting radio waves. So yeah, so it's interesting. So L could be really small. It depends like how long we end up lasting in our current state. So a lot of it's kind of gets really into kind of philosophical territory there. But but the end result of this equation is that it gives us N. And like I mentioned, that's just a very rough estimate for the number of civilizations that we might be able to detect in our galaxy. And yeah, so this isn't an equation like E equals MC squared or something like that. It's not a specific, it's not going to give you a specific accurate number, because truthfully we don't know what most of these numbers are. And it gets into a lot of like guesswork and really interesting kind of discussions every time that you kind of try and pin down one of these numbers, because you can't, we don't have enough information about life beyond Earth, because we're the only example that we know of. But I think that the Drake equation is just really fascinating, because it kind of guides us in our thinking of what are the different factors involved in how life evolves, and whether it might be common or it might be rare, because we really don't know. We need more data to find out. But anyway, so this equation, which is now like probably one of the most famous equations in astronomy, it started in Green Bank, and Frank Drake kind of came up with it as he was preparing for this conference. So of course I talked about the Tatel telescope, or 85-1. So the reason that its alternative name is 85-1 is because there are now 2 other 85-foot telescopes at Green Bank, and they all work together as part of an array, which means that it's a bunch of little telescopes working together as one big telescope. And it served as a test bed for the very large array in New Mexico, which is a much bigger interferometer with many more dishes. And it's currently, doing lots of cool research out in the desert. So yeah, but the Green Bank interferometer, even though it's kind of small for an array, it did some really fascinating science. Unfortunately, it's no longer active, mostly due to lack of funds. So theoretically, if more money magically became available, it could potentially be resuscitated. But yeah, so it was composed of 3 main elements, the 3 85-foot telescopes, and then an additional telescope was used initially 26 miles away in Huntersville, West Virginia, to test kind of long baseline interferometry, which is when you kind of spread out all the elements of the array really far, which gives you better resolution. So in 1974, using this instrument, a couple of radio astronomers discovered the compact radio source at the center of our galaxy. So what's that? That's actually the black hole, Sagittarius A star. So folks at Green Bank were actually, or folks using telescopes at Green Bank were actually responsible for kind of really figuring out or finding proof that we have a black hole at the center of our galaxy, which is a huge deal. So I just thought this was really neat, especially with kind of the Event Horizon Telescope kind of taking this really cool image of Sagittarius A star earlier, or was that earlier this year? That was last year. And so just the comparison of these two maps is just pretty impressive. Like you can see this very kind of uh, early stages of looking at that radio source, and you can see this really zoomed in, beautiful, kind of detailed image. And so in a kind of a cool way, the research with the Green Bank Interferometer kind of paved the way for this really amazing Event Horizon Telescope result. So yeah, so moving right along our line of telescopes to the 140-foot telescope. This is yet another favorite of mine. So it was finished in 1965. It's the world's largest equatorially mounted telescope of any kind, and it will probably stay that way because it is really, really hard to build large equatorially mounted telescopes. And you can see the design on this thing is crazy. It has what I believe is the largest ball bearing in the world in this right here in this kind of curved structure. And so the reason that they built it equatorially mounted is because it was much easier to do the computing for the coordinates, because when you build an altitude azimuth telescope, you have to track, of course, in two directions, and that's computationally intensive. And in the 60s, when the computing power was kind of limited, they decided to build this equatorially mounted telescope so they could only track in one direction, and kind of minimize the computational complication. But as computers became more advanced, it became much less practical to build equatorially mounted structures, which are of course kind of asymmetrical and difficult to build. And so people kind of started building more of the altitude azimuth telescopes. But I think this thing is just a really fascinating kind of relic of that earlier time, and it's just really a pretty instrument. You can see kind of the base of it kind of looks like a ship because it was built by a company that built mainly ships. So yeah, so that's definitely always a kind of a favorite of people that visit just because it's so amazing. And it's recently been in use. It was actually last used as a downlink station for Radio Astron, which was a radio telescope that was actually in space. It was a Russian satellite. They were doing very, very long baseline interferometry. So they were actually using, a telescope on Earth and a telescope, out really far in space. I can't remember the exact location. But yeah, so that was just kind of really interesting project. And through its history, the 140-foot telescope discovered lots of molecules in space, things like formic acid, which you find in insect venom, methanol, acetaldehyde, fumble over these, which of course is chemical responsible for hangovers, cyanoacetylene, again, I'm going to mangle these horribly, and that's a possible precursor to the DNA acid cytosine, or cytosine, so yeah, moving on. But yeah, so that's
You're doing good. Hang in there.
thank you. So yeah, so that's really rich history there. Unfortunately, it is also no longer in use, but again, that's another funding issue. So if the funds became available, it could totally be kind of revamped and used probably to do more molecular research would be a great application for it. But yeah, keep our fingers crossed that someday that'll be possible. Yeah, so another telescope that I wanted to talk about is the 300-foot telescope. This one is also kind of famous, not so much because of what it did for when it was alive, but because of the kind of catastrophic way that it collapsed. So it was actually built in 62. The 140-foot telescope, because it was so complicated, took forever to build. So they decided, okay, we got to start doing some more research here. So they just kind of basically threw together this 300-foot telescope with the anticipation that it would only last like 25 years or so. They didn't design it to be long lasting. They designed it to be quick. It was a transit instrument, only tracks in one direction, or only steers in one direction. Otherwise, you have to kind of wait for objects to kind of move overhead. And yeah, so right after kind of the expected 25, 26-year time frame that it was, predicted to last, it ended up collapsing due to a metal failure. And so that was that kind of made the tabloids. People said, oh my gosh, it's been zapped by aliens. Of course, obviously it was not zapped by aliens. It was just a piece of metal that failed. But yeah, so there was actually a guy. So this building under here, the brick one, is actually the control building for that telescope. And there's actually a guy in there, the operator, at the time that it collapsed. Yeah, his name was Greg Monk, and he was actually fine. Thank goodness. But yeah, so the receiver of the telescope actually kind of fell onto the building into the bathroom. So if it was just lucky that he was at his desk, because otherwise, that would have been a pretty bad day. But luckily he made it, and he's still an operator there today. So that's pretty. He's a really neat guy. So that's glad that that the building kind of held up. It was yeah, quite interesting. This was in 1988. So of course, with the collapse of the largest telescope on site, that kind of raised a lot of interest in the idea of building a new telescope. So in the early 90s, they started construction on the Green Bank telescope, and you can see here the work on the foundation, and then they kind of used cranes to kind of build up the structure. So the Green Bank telescope is currently kind of the premier telescope at the observatory. It's a super fantastic instrument. And yeah, it's really unique. So it's the world's largest fully steerable telescope of any kind. It can observe 85% of the northern sky. It's massive. It's 100 meters by 110 meters across. It weighs 17 million pounds. And it covers a huge range of frequencies from 0.3 to 116 gigahertz. But one of the really kind of unique and special features of it is that it has tremendous sensitivity because it has an unblocked aperture. And that just means that instead of the arms that hold up the radio cameras or the receivers being in the middle of the dish, they're off to the side. So that means that the whole dish is unobstructed, and you get fantastic sensitivity. So next part of the talk, I wanted to kind of cover some of the technical aspects of the GBT. Let's see, I can see a chat message here. Aliens, yep. I like that. Yeah, they don't want us to find them. No, we still haven't found them. Gosh darn it. Yeah, so this next part of the talk, I wanted to kind of cover a little bit about the technical aspects of the telescope. And so a lot of times I do this presentation with middle schoolers, so I try and get them to think about the telescope and give me suggestions for what are the things that they notice. But I'll just go ahead and kind of flip through these. So these immediate things that you notice about the telescope, of course, it's big, it's heavy, it's sensitive, it's made of metal mostly, and it's asymmetric. It's lopsided compared to the other telescopes that we've looked at. And these are all, even though it sounds kind of simple and almost silly, these are kind of the fundamental things that are important about the telescope and why it works so well. So how does a radio telescope work? Well, in many ways, it's a lot like an optical telescope. You have your radiation coming in, bouncing off your parabolic reflecting surface. A lot of times there will be a secondary reflector that'll bounce your radio waves off into what we call a feed horn, which kind of funnels your radio waves to the radio receiver, which again is your radio camera. And from the receiver, the signal then basically turns into a current. So the radio waves kind of induce a current in the antenna cable, and then it kind of travels through to the electronics, which will amplify it, make it stronger, because of course radio signals are very, very weak when they come in from millions of light years away or however far away they're from. And then so after your signal gets amplified and such, then goes through gets digitized, and then people can actually kind of analyze the signal using their computers and such. So this is just kind of a cool diagram of the GBT. I won't dwell on this too long because I have some other things I'd like to get to, but yeah, you can just see that kind of the different parts are labeled. And yeah, so I've actually been kind of all the way up this structure to this point here, which is the top of the receiver room. So all the a lot of the radio cameras are in this little spot right here. And so, yeah, that's both terrifying and absolutely amazing because you can see like the entire valley, all the other telescopes. It's just, once in a lifetime kind of thing. I've also stood in the dish, which is completely terrifying. And I'll show you a picture of the surface and you'll kind of see why. But yeah, so why is the GBT shaped like that? So I kind of talked about this already. But basically the reason that it's shaped the way it is so that the feed arm here can be mounted off to the side instead of in the middle. And why is that important? Because first of all, it increases aperture efficiency. It means that more radio waves are coming straight to the dish instead of bouncing off of your kind of structure over top of it. And the other thing that's cool about it is it reduces reflection and diffraction, because if you look at this telescope in the background here, which is actually the 140 foot, if you have like kind of extraneous radiation, like radio frequency interference that you don't want to detect, those structures that are over top of the dish can actually bounce that unwanted radiation into the dish. So that's not cool. So that's why the GBT was built the way that it was. And it was really, really difficult engineering wise because it was asymmetrical. It'd never been done before. But it's ended up kind of being like a pathfinder for other radio telescopes that have been built at a smaller scale. So it's really groundbreaking. So the reason the dish is big, this is again very similar to the reason that you want big optical telescopes. You get better sensitivity and you get better resolution. So the bigger your radio dish, the finer the detail you can see in your maps. So I'm just realizing that I've kind of taken a long time at the first part of my presentation, so I'll try and speed through some of these slides. But so what's it made of? The panels are actually made of aluminum. Structures made of steel. So you can see all these like individual beams that are kind of holding up the dish. Those are all individually welded. So the track is really cool. It's made of concrete, steel, a lubricating layer of bronze, Teflon, and molybdenum, and epoxy grout. And we'll talk a little bit more about each of those kind of parts. So weather, these are questions that I get a lot about the telescope, is how does weather affect the telescope? So wind, of course, is a concern because it's basically a giant, wind sail. So you want to be really careful about wind. So when you get above 30 miles per hour to 40 miles per hour, you have to stop observations. And if it's sustained winds, then you have to turn the telescope into survival position, which means that basically its back is to the wind and it's kind of at the optimum position where it won't get kind of bounced around too much. Snow, if you get too much snow on the dish, then basically you just tip it over, dump the snow off. It's called a snow dump, not surprisingly. So ice is another issue. So if ice accumulates on the dish, then you have to stop observing, put the telescope in its kind of survival mode. Temperature. So if you get to really low temperatures, you have to slow the telescope down due to some properties of the grease and azimuth bearings, which I actually have to do a quick show and tell here. I have an azimuth wheel bearing from the telescope. This used to belong to one of my mentors. And then one of my coworkers actually gave it to me. So it's really cool. It's also super heavy. So lightning, you would think that this would be a huge problem, but actually it's usually not, because the structure is super well grounded, because people knew this would be a problem, so they prepared for it. So water vapor can actually be a problem for some frequencies, not all. But yeah, so you just have to be careful and kind of like plan for dry days if you want to do certain frequencies of observing. All right, so this is a picture of the surface, and I think you can probably see like why it might be terrifying to stand on. The other reason it's scary is that the panels are really thin, so you can kind of feel them squishing under your feet. So it's really an amazing part of the structure, and really beautiful. So it's made up of 2004 individual panels. They can all be adjusted so that the surface overall can be flattened out to the point where any deviations from a perfect parabola are less than the thickness of a business card. And this is accomplished through 2,209 actuators that control the corners of the panels. So there are about 20 something different molds of panels, so there's different shapes. And I think the paint is really neat, which is a really kind of nerdy thing to say, but the paint is actually white invisible wavelength, so it reflects sunlight, but it's transparent in radio. So the radio waves just go straight to the metal instead of like getting messed up by the paint. So I think that's really interesting how they kind of did that and chose that paint. So homologous design of radio telescopes. I'll come back to this if we have more time. It's an interesting concept, and so if somebody wants to know more, please ask me about it. Yeah, so actuators, just wanted to show a close-up picture. Yeah, so that's what they look like. Pretty cool little instruments. So the GBT's azimuth track. So the track has an interesting story. It was originally built with much smaller bolts and a different design of the plate. So the track is covered with what we call wear plates. And those are kind of that's just the top layer here. And so they were initially shaped so that it was just kind of like a diagonal line. So just kind of a diagonal edge. So what ended up happening, because there were not enough bolts and there was this diagonal shape, it ended up kind of like when the telescope would go over it, 17 million pounds of telescope moving on this thing. It would basically bunch up like a carpet and kind of like shear, the panels would like shear off next to each other. So that was a problem. So they ended up redesigning the track, adding a whole lot more bolts, making them bigger, and instead of having like a diagonal shape to the track parts, sorry, the wear plates, they would have they've created a chevron shape, so that basically helped with that kind of problem. So kind of rushed that explanation. So if you want to know more about the track, I'm happy to kind of say it in a more clear way. All right, but I wanted to make sure that we got to the science because this is really cool. So there's a lot of different things that we study with the Green Bank telescope. So pretty much any astronomical subject that you can think of, the Green Bank telescope has touched in some way. It does lots of really neat stuff. So this is just kind of a scattering of pictures that are related to the telescope's work. So one area of research that GBT focuses a lot on are pulsars. So pulsars, of course, are the remnants of stars that are when stars that are between 10 and 25 solar masses die, they explode in supernovas, then they become pulsars. So pulsars are very, very small, very, very fast spinning. So they spin really, really fast, and their rotational periods are very predictable. So they were discovered in 1967 by a radio astronomer called Jocelyn Bell Burnell. And it was found that they emit radio beams from their poles. So that means that we can detect them as basically repeating blips in the sky. So they're basically Carl Sagan kind of described them as like cosmic clocks, like cosmic lighthouses, which I think is really cool. So because pulsars are such precise clocks, we can actually use them to test relativity in a lot of different ways. And so when we look at a pulsar, we can measure when their pulses come to us, and if when those pulses arrive is different from what we would expect based on no disturbances in space, then we know that something weird is going on. So astronomers actually use this property to try and detect gravitational waves, because if the pulses come to us in a way that is delayed in a very specific way, then that basically allows us to say, okay, that they're delayed because a gravitational wave has come through and kind of basically displaced it and caused it to take a different amount of time to reach us. So at the time that I wrote this slide, this discovery had not been confirmed, but now we can say that actually pulsars have been used to discover the gravitational wave background. So it's kind of unlocked a whole new area of radio astronomy and physics in general, which is so cool. And yeah, I wish I had more time to talk about that, but got to talk about some more areas of science. So actually there's some other ways we can use pulsar systems to test relativity. Again, I'll come back to this if anybody has questions. So fast radio bursts are another mystery that has kind of come up kind of just serendipitously. So back in 2007, astronomer Duncan Lorimer, who and his student David actually found this really weird burst signal, just kind of a random burst, just like a blip in their data. And it was kind of a one-off thing, and people were just kind of like, well, this is probably like interference, this is probably like some sort of human-made signal that it's just gotten into our data. It's probably a microwave oven. Even Duncan's wife, Maura McLaughlin, who is an astrophysicist and actually made this discovery, along with a huge team of other researchers. She was kind of originally on team microwave. She kind of thought it was like interference, but Duncan kind of like kept looking into it, and eventually they found more of these weird blips, and turns out they were not microwave ovens. They were signals from other galaxies, and we still don't quite know what they are. They could be from some sort of weird type of pulsar. They could be, it's hard to say. People initially thought, well, is it aliens? But because we're seeing so many of them from so many different places, and because they look pretty natural, it's probably not aliens. But always cool to think about that. So measuring Hubble's constant, I'm going to kind of race through this little part here. Again, that's another thing I'm happy to come back to. It's an interesting kind of cosmology project, but yeah, so I did want to mention, of course, the GBT is continuing the work that was done by the 140 foot to discover lots of new molecules in space, including kind of the first evidence, or well, including benzonitrile, which is a precursor to a polycyclic aromatic hydrocarbon, which you'd have to ask a chemist exactly what that means, because I'm not totally sure, but it has to do with, it's basically just finding more and more complex carbon chain molecules, which is always like promising when you start thinking about the search for life in space, because as you find these more and more complex molecules, you kind of approach the level of complexity of like amino acids and things like that, which is really cool. So yeah, so this is a fascinating project. This is kind of the continuation of Frank Drake's early work. So the Green Bank Observatory has been involved in SETI, of course, since the 60s, several projects since then. The most recent one is Breakthrough Listen, which is the largest SETI project to date. It's a $100 million project funded by Yuri Milner, who is a billionaire from Russia. The project makes use of GBT, the Parkes telescope in Australia, along with several other radio telescopes, with the goal of searching like lots and lots of stars and galaxies for signs of extraterrestrial life. And they release their data openly, so anybody can kind of look through it and like try new algorithms and things. I worked for them for a summer. It was really cool. And yeah, so because the Green Bank telescope is collecting so much data for Breakthrough Listen, it's possible that we've discovered alien life, but we don't know it yet because we've not sifted through all the data. So it's really exciting. So I'm getting real close to the end here. Thanks so much for your patience. So the DART mission is another really cool thing, probably several of you have heard of. So basically the idea was to send a spacecraft out and have it ram into an asteroid and deflect its course as kind of a test for, future planetary defense work, to try and, if there's actually a Earth life threatening asteroid coming towards us, what are we going to do about it? Well, we would have to deflect it in some way. So this was kind of like a very early stage test. It was actually hugely successful, and the GBT kind of helped track the trajectory of the asteroid after the DART mission kind of rammed into it. So that's quite interesting. GBT does lots of other planetary defense work as well. So yeah, so that's kind of a very, very quick and non-comprehensive overview of the science done at the GBT. So the other kind of key part of the observatory, and possibly my favorite part, is the work that they do in outreach and education. So they run several programs for students, people of all ages. They have an annual festival called StarQuest, which is great for amateur astronomers. If any of you want to go, highly recommend it. They have it every summer. And yeah, so they host lots of camps, lots of like undergraduates do research there. I did research there starting as a high schooler. And yeah, so also, so if any of you are in West Virginia on September 24th, they're going to have an open house day, which lots of exhibits, cool things to do, kind of behind the scenes tours that you don't usually get. So yeah, so mark your calendars for that. I don't think it's been announced on their website yet, but it's going to happen, and it hasn't happened since before COVID, so that's super exciting. And I'm going to be there, so if you go, I'll see you there. So yeah, so here's just kind of a list of links to check out if you're interested. Lots and lots of things to do. Also, for those of you who mentioned you're ham radio operators and into like maybe getting into like some amateur radio astronomy, they have a conference for the Society of Amateur Radio Astronomers every summer, and which is a great group. And yeah, so lots. I always learn a ton when I go to those conferences, because there's just people just are, you know, have crazy amounts of knowledge. So yeah, so thank you very much for listening to that long-winded presentation. And if there's any questions that you have or any slides that you want me to go back to that I kind of skipped through, then let me know and I'd be happy to.
You've got a couple of questions in the chat, Ellie. You want to take a look? I think one of them, what are the panels made of?
Yeah. All right. Okay, so I've got one here. The first one is a direct message. So I'll and the question is the detector actually at the focal point? That is an excellent question, and the answer is yes, sort of. So I will go back to this diagram, and this is something that I kind of glossed over initially. But yeah, so you can see in this diagram where kind of things are. So so there's two different places where the receiver can be mounted, or aka the detector. So this thing right here that looks kind of like a boom, this is called the prime focus receiver. So when it's on a retractable boom, so it can actually swing back here. But when it's out, that is at the focal point. So the radio waves coming here, they bounce off here and they go in there. But if you want to use a different set of receivers, there's also receivers mounted right here. You can swing this thing back so that it's out of the way. Then the radio waves will come down here, they'll bounce off, and then they'll bounce off this thing here, which is actually a subreflector. And then they'll bounce down here, and there's radio detectors right here. So that's so yeah, so they're at the focal point, but you just kind of like adjust where that is based on yeah, which set of receivers you want to use. So there's actually a turret here where there's eight receivers mounted, and you can rotate them so that whichever one you want to use is actually at the focal point. So yeah, so hopefully that answers the question. If not, feel free to follow up. Let's see. Okay, so there's a follow-up, but you can adjust the 2000 panels. Yes, you can adjust the panels. So that basically just gives you a really crisp, clear image. So of course you point your telescope to get like on your proper location, and then you adjust the panels to correct for any like deviations that happen. Like when you tilt the dish, it'll sag due to gravity. Like temperature will kind of like mess it up. So it'll cause like different parts to expand. And so that's kind of like what the actuators help correct, is any kind of like deviations that happen from moving the telescope and from like weather change or like temperature changes. So yeah, so hopefully that kind of helps. Let's see. Okay. So what are the panels made from? So the panels are made from aluminum with that really special cool paint that I talked about on it. And yeah, so great question there. So how many of the radio telescopes are operational at Green Bank now? Okay, good question. So, and there's actually more telescopes on site that I didn't even have time to mention. So of course the Green Bank telescope is the main one. It's like overbooked. It's used like 24/7 except when they're doing maintenance. or things like that. There's also a 40-foot radio telescope, which is used completely for education. It's got like an underground bunker with like chart recorders and like a switchboard and all this other stuff. So if you visit Green Bank, like for the Sarah conference or whatever, you can see that. That's really neat. So there's a 20-meter telescope on site that's you can operate it remotely. It's part of the Skynet program, which allows students again to use it. It's also used for there's some contracts with different groups that use it for other purposes as well. So there's also kind of like just a scattering of like little like test projects. So because it's in the quiet zone and because they have such a well-staffed facility, different like universities or observatories will kind of like bring their equipment there to test. So there's like different little collections of antennas all over the place. I installed one actually, which was really fun. In addition to that, they have CHIME. So CHIME is short for the Canadian Hydrogen Intensity Mapping Experiment. And so of course the main location for that telescope is in Canada, but they installed a second kind of version of it in Green Bank so that they could like be observing in two places at once and get like a really good baseline and kind of like triangulate the sources that they're looking at. So the CHIME telescope is actually mostly focusing on discovering new fast radio bursts. So that that weird signal that I talked about that Duncan Lorimer discovered. So CHIME is mostly focused on that. So how many said I've lost count. So it's the GBT, the 40-foot, the 20-meter CHIME, and then just kind of like a scattering of other like instruments on site. So like 4 to 5-ish. But that's kind of like always updating because there's so many cool things going on. All right. And then Bill Wilson says very informative. Thank you. Thank you very much for the kind comment there. So visual is okay. So this question is visual is image based typically. Radio astronomy is a single pixel. Excellent question. So this is something that I should have clarified earlier on. But yes, so in general, when you're using a radio detector, it will be a single pixel. However, there are some radio detectors that are being developed and that are currently in use that are multi-pixel. Like the GBT has one receiver called Argus, and it has 16 beams, so it has basically 16 pixels. But it's just a bunch of like little feed horns all like bunched together. So it's it's still like a bunch of like single pixels working together. Yeah. Oh, and I see that Rick answered that. That's great. Yeah. Yeah. So that's fantastic. Yeah, the raster scan, that's exactly right. So when you want to do a map, of course you have to go like slowly, like back and forth, to get your image. So yeah, so great question and great answer from Rick. All right, so there's a question here, is Arecibo still operational? Sadly, it is not. So yeah, so I think that it kind of got structurally a lot of damage to it during a hurricane at some point, and then I think later on, unfortunately, it had kind of like a catastrophic metal failure. And so basically the receiver kind of swung down and fell through the dish. And so it's basically not operational anymore. And I think they've closed the site for now, but I think they've talked about reopening it as an educational facility. And there has been talk of installing a new radio telescope on site, which I really hope that they do. Because I've never been to Arecibo, but it just seems like an amazing site with a lot of really talented people there, and it's just a huge shame what happened. So yeah, so thanks for that question. But yeah, so Arecibo actually was a big partner on that gravitational wave project that I talked about. So when it collapsed, basically the GBT was the main remaining instrument that was involved in that project. And so yeah, so that just put a lot of pressure on the GBT in terms of like kind of taking up like a lot of the observing projects that were done on Arecibo. Of course, the GBT is already oversubscribed, so it's really makes a good case for, you know, more funding for more telescopes, which is always, you know, a struggle. But oh yeah, I see a comment here. It says I knew one of the principals. Yeah, I assume that's for Arecibo. Yeah, uh that's interesting. Thank you for sharing that. Yeah, so let's see. Yeah, so a couple of folks that used to work at Arecibo kind of moved to Green Bank to work for a few years as adjuncts. All right. So here's a question. You mentioned 8 detectors available. Which is the most commonly used? Ooh, that's a good question. So it covers the full range from 0.3 gigahertz to 116 gigahertz. So I don't know the exact numbers, but my guess is going to be that the L-band receiver is the most commonly used. And that's because it covers 1.4 gigahertz, which is the hydrogen line. And of course, the neutral hydrogen line, which Rick was talking about earlier, is the emission that you get so if you have a neutral hydrogen atom where you have 1 proton and 1 electron, if the electron undergoes a spin flip so that its spin is opposite to the yes, exactly. So if it undergoes that spin flip towards it's spinning in the opposite direction as the proton, then that emits radiation at 1.4 gigahertz. And of course, since hydrogen is the most abundant element in the universe, it's everywhere. That signal is everywhere. And so that's a really, really commonly used receiver. And so my guess is that's probably the most commonly used one. Great question. All right. Here's a comment. Very cool. Yep, built a scope in high school. Do you mean a radio telescope? That's really cool. Yes, neat. Okay, that's really cool. I built a radio telescope in high school too. It's radio telescope, loosely speaking. It was like a loop antenna that you could use to detect like solar flares, which is neat. So what kind of telescope? Did you build like an actual like proper radio telescope, like a dish? Oh, I'll give you a second to type. Sorry, I'm firing questions. I'm supposed to be answering. So yeah, so thank you for the kind comments there.
30-foot Yagi.
Oh,
Right.
wow. Neat. And were you like looking for like the radio lobes from Jupiter, or were you looking at something else?
Here, let me go audio. It's easier.
Cool.
No, it was a science fair project in high school.
Neat.
And yeah, we were just doing very simple stuff, trying to map
Yeah.
simple intensity as the sun or the moon or something else would traverse across the beam of the array.
Oh, how cool.
Yeah, it was kind of fun. It worked. And if you want a great FM, you could point it at any radio station. It didn't matter what you were tuned to.
Neat. That's really cool. That sounds like a great project. Yeah, so one of the things that I'm kind of involved in that's kind of, it's not exactly functional right now, but it's kind of like an not archive, it's still active site, but open source radio telescopes is something that I worked on. I'll put the link here because we just kind of linked to a bunch of, type open source radio telescopes.org. We have like plans for some simple radio telescopes, including like a horn, like for H1 detection, Rick. So yeah, so there's some plans linked from there. There's also a program called DSPIRA, which if you Google that, I can't remember the exact website name. That's digital signal processing and radio astronomy, but it's for teachers to use. So that's really where you get the good horn antenna plans. So yeah, so those are some
Hack
cool groups.
One RF SDR too. So
oh yeah,
yeah,
cool.
I have several SDRs I'm playing with. That's I need an LNA and a dish or a horn to start playing with it.
Oh, that's neat. Do you have like what software are you using?
Well, I have GNU radio, and
Yep.
and there's
All right.
and I also have for most of my ham radio stuff. I try to do a spectrum. I use this one of my SDRs is basically a spectrum analyzer
Yeah.
in the ham bands that I'm working. And for that, I use, what's it called? SDR console. So,
Okay, that's cool. I'm not familiar with SDR console so much, but GNU Radio, yeah, my first research mentor, who was Richard Prestige, who was an astrophysicist at Green Bank, that was kind of one of the first things that he taught me how to use was GNU Radio. And the project that I did with the Berkeley SETI Research Center was to implement a GNU Radio control system for the Allen Telescope Array, which was really fun. So, GNU Radio is great. But yeah, that's neat. So like, so is the horn antenna your next plan for your kind of like radio astronomy stuff?
yeah. Well, okay, let me kill this background thing. It's keeping anything else from working. All right, so this is my computer station. This is my ham radio station.
Oh, cool.
There's my SDR that I use for the spectrum analyzer. And
Nice.
that's all hooked up to an antenna array outside. And
Oh, how neat.
so, but yeah, I need to build a horn, build an antenna of sorts, and I'm already logged into your open source
Oh, good.
antenna site, and I think I found this before, and
Oh, good.
I'm gonna follow up with that. It's a project I want to do.
Yeah, that's neat. I've had like a half-built horn sitting in my brother's in my tree house out in the backyard for like years now. So I need to like actually build the electronics, but it's just sitting there right now. So
Amazingly, the electronics for this stuff is often quite cheap. It's
yeah,
all satellite equipment, or and of course the Chinese produce these boards that are just ridiculously cheap. You can get on
yeah.
eBay and find them, and it's not an expensive hobby.
No, it's really not bad at all. Pretty nice.
A lot cheaper than my other telescopes.
Yep. Yeah, I should have included that on the slide of like benefits of radio astronomy is like it's cheap. At, at least when you're doing it amateur, I guess not so much when you're building giant asymmetrical dishes, but
Right. Well, listen, this has been a wonderful presentation, and thank you so
thank
much
you.
for joining us. Has anyone else got any more questions? So is this your career? What are you doing now?
Yeah, so right now I'm working for a nonprofit called West Virginia Alliance for STEM and the Arts. So the main project that we're working on right now is something called Steam Trek, which is a video game that's the purpose of it is to like get it's basically kind of like a virtual like activity fair. So we have like different like virtual tables set up like with information about the Green Bank Observatory, local art museums, local like science museums, things like that. And kids can kind of like wander around like as an alien. They have a little alien character and they can like wander around and like look at all these learning resources.
So
We
when
have
you
like
say STEAM, it's the science, technology, engineering, and art and math
yes.
acronym. Yeah,
Yeah,
cool. Very cool.
exactly. Yeah, so that's so I'm working on that right now and planning to get kind of like back into some more astronomy stuff as well. So probably going to start a master's in physics here soon and then potentially extend that to a PhD. We'll see. But yeah, so that's just kind of like figuring stuff out. But yeah, definitely still radio astronomy is still definitely a big passion of mine, something I'm gonna keep working on. So
And do y'all do
yeah.
a master's at Rhodes?
Oh,
No, we do not. Sorry.
oh, that's really interesting. And like I said, I'm super fascinated to hear about all the stuff that you guys are doing with the club. So we have some groups around here in West Virginia, and yeah, like I said, I'm taking notes.
Well, feel free to get in
what you all
touch
are doing.
anytime,
Okay.
Jeremy or me, or look at our YouTube channel and see what we've done for meetings and stuff. And
Yeah.
we love to help spread the word. So hang in there, and thanks a bunch.
Oh, well, thank you. It's been wonderful. And yeah, again, thank you all for having me and for yeah, for all fantastic questions and for the good company. So I appreciate it.
Well, all right. If that's it, that's all I've got. Is anyone else got anything? Very good. Y'all have a good evening and a good weekend. Y'all take care. Observing is likely going to be on tomorrow night. The weather is looking pretty good. It cooled off about 10 degrees here yesterday. And no, that was today. Late last night, it started going down. So it's bearable weather. So look forward to seeing folks tomorrow night at the observing session. Good night.